Thank you, Fred. Recording in progress. Ladies and gentlemen, hey, thank you for joining me today on a topic which is all about reliability life models. So this is a really interesting topic. I mean, there's so many different parts of reliability engineering, but perhaps none more so fundamental than linking the causes of failure with failure events. And how we do that, or how we represent our understanding of how that happens, it's with reliability life models. And I'm going to start with a really an example or a case study that I really like. It is such a good way of seeing how reliability life models, or even just a basic understanding of how cause and effect influence failure, can make our life really useful. So we often come across this sort of sentiment here when we're in the field of reliability engineering, where someone might say that using probability distributions to get information from data is great, but an often heard complaint is that sometimes this gets in the way of us using our brains. Our brains are amazing. Our brains have all sorts of wonderful corporate knowledge, all sorts of fantastic fundamental understanding of how things fail. It's actually a great shame that we sometimes rush to statistics and probability and ignore what we have already learned over the years. So, for example, let's look at a Ford F-150 truck. Now, a Ford F-150 truck is like most vehicles that on the road today. It moves along the road and it converts kinetic energy to the road with friction between the tire and the road surface. But of course, that's well and good when you want to go faster. But when you want to slow down, then we need another transfer of energy from kinetic energy back to friction through our brake pads on our brake discs using calipers like this one. So a brake pad on a vehicle like an F-150 is all about converting kinetic energy to thermal energy. And that is how we slow our vehicles down. And these brake pads will eventually wear away and need to be replaced. So if a brake pad wears away, technically it's not a failure event, but it really is quite similar to some of the reliability engineering stuff we do, because we need to understand how fast damage accumulates to help us understand when we need to replace these brakes. And as is one of my trademarks, I'm going to now reintroduce the random hand of failure, which, if anyone's been to any one of my webinars in the past, you should be getting quite familiar with the way I attempt to characterize a random failure process with this hand here. And this hand incorporates all the different things that will influence how long it takes for our brake pad to fundamentally fail. And some of the factors in this scenario include material imperfections in the brake pad material, the starting speeds of the vehicle itself, the vehicle mass, and the finishing speeds. We can go through or wear away brake pads much faster if we drive aggressively. We can wear through brake pads much faster if we are always carrying heavy loads. So we have that much more kinetic energy to lose through friction. So we have an understanding of what drives failure, but we might not be able to say with absolute precision when our brake pad will fail. But that said, if we can learn more about or predict with greater accuracy when our thing will fail, that is very useful. Okay, so we know that if we were to get a lot of data and perhaps use something like a histogram, we could get a relatively good understanding, perhaps if we have lots of information, about the relative density at which in this case, brake pads are starting to fail in terms of miles to failure. And we can also, if we were to hypothetically study our failure process ad infinitum, we would eventually arrive at a probability distribution, probability density function, I should say, or PDF, just like this bell curve. And this bell curve represents a state of total knowledge, where if we have tested our brake pad in every scenario, in every possible vehicle known to humankind, and we've had an infinite number of data points, we get this wonderful PDF curve. But of course, the real world isn't quite like that. So, but hypothetically, if we were able to identify this PDF curve, we could, for example, work out when 10% of our brake pads will fail or have worn too thin. And this is analogous to lots of other maintainability and maintenance scenarios where we're trying to understand when we should replace gaskets or change oil, or in this case, change our brake pads. Is it okay to replace our brake pads here? Let's just say we're happy with, on average, 10% of the brake pads in our vehicle fleet or on a certain type of vehicle failing by the time we change those brake pads. If 10%'s okay, then this is when we can swap those brake pads out. If it's not okay, then we need to find the risk of brake pads wearing out prematurely, and that then drives when we should replace our brake pads. If we can tolerate more than 10%, then we can have a longer interval between brake pad replacements. If we can't tolerate 10%, we need a shorter interval. But regardless of whatever interval we come up with, we are also throwing away, when we arbitrarily replace something because it hits a servicing interval, we're arbitrarily throwing away brake pads which still have some residual life. So if you want to minimize the chance of brake pads prematurely wearing out, the problem with that is that while you're servicing or replacing brake pads more often, you're throwing away more and more brake pads which have residual pad thickness or pad material. So let's look at this from a slightly different perspective. We know that brake pads start with a certain amount of thickness, and over time, when that vehicle on which those brake pads are attached drives, the brake pad material will eventually wear away. And so failure occurs when a certain amount of brake pad material is no longer present. And of course, the trajectory of each vehicle was unique based on all those things we talked about, based on driving behavior, based on speeds. Does a vehicle do lots of highway driving? Does it versus lots of urban driving? Does the vehicle have a lot of load in that tray, or is the vehicle just an exclusive passenger vehicle, so on and so forth? So for example, this line over here might represent a vehicle which has consistently got a heavy load in the tray. This could be a tradesperson's vehicle. And this line of degradation or wear over here might be for a vehicle where the person or the driver tends to drive very slowly, like my father-in-law, who owns about 3 or 4 Mustangs, but hates going anywhere near the speed limit. So we can see clearly here that there are different ways or different patterns in which brake pads wear away. And so we can't easily attribute everything back to miles to failure, because it doesn't, miles itself, the distance a vehicle drives before you replace those brake pads, doesn't take into consideration all those other things we just looked at, like speeds and masses and driving behaviors and so on. So let's just say we're trying to better understand brake pad wear for the purpose of perhaps optimizing our servicing interval where we replace these brake pads. And so we'll go back to our Ford F-150 and really examine this wear process in greater detail. Now, if I represent the velocity of my Ford F-150 as it's being driven with a line where the higher the line is on this illustration, the higher the velocity of the vehicle. Well, when we accelerate, the velocity increases, but when we have a braking event, the velocity decreases. So hopefully this little graphic or animation conveys that point. So every time we use our brakes to decelerate from a higher velocity to a lower velocity, we go through what's called a braking event. And one of the characteristics of this braking event is the decrease in velocities we experience. Now, we know from basic physics we learn in high school that the amount of energy this equates to is the mass of the vehicle multiplied by the difference between the squares of the velocity divided by 2. So this gives us an equation which tells us how much energy our brake pads had to disperse. So we might be able to, let's imagine we have an onboard computer which is able to monitor different velocities of our vehicle. Now, that might mean that the computer can work out the different velocities and say, hey, I know what the energy is as long as I know the mass of the vehicle. Now, we of course know what the mass of the vehicle is when it's unladen, but how do we know the mass of the vehicle with all its different loads and passenger configurations? We really can't truly understand the amount of kinetic energy we lose when we have a braking event unless we know the mass. Well, that's where Ford has done something really, really cool. And they're able to include sensors where if we go back to the acceleration event, the onboard computer is able to work out how much power was transmitted through the wheels as part of this acceleration event. And this means that if we know the power and we see how much power is required to accelerate the vehicle to a certain velocity, we can estimate the mass of the vehicle every time the driver steps on the gas. So this means that over time, regardless of the load, every time the driver steps on the gas, the vehicle is able to re-estimate total vehicle load. And so once that happens, we're able to now make much better decisions about when to swap out brake pads, because we know that the amount of energy our brake pads dissipate is a much better unit of use than miles. So when Ford did this, when they compared these vehicles which were accumulating damage at these particular profiles over here, where we were simply tracking the amount of brake pad wear with respect to miles, when they changed the perspective from miles to braking energy, this is what happened. Now you can see that the profiles for each vehicle are now a lot closer. And what that means is we have a ton more information. So we are able to, if we're able to track the amount of the cumulative braking energy from each vehicle, which onboard sensors can now do, then instead of having to deal with a very wide PDF, which describes how long it takes for our brake pads to wear out, we now have this very narrow PDF because there's a lot less uncertainty, which means that we only change out brake pads essentially when we need to. And when we do swap out those brake pads at a certain interval of cumulative energy dissipation, the ones that are left, because this model is so close to the actual degradation properties, the ones that we do throw away are more likely to have just a tiny bit of wear life remaining. So we save money. We don't have to replace brake pads as often. We understand what's going on. In fact, we could potentially even have in the future onboard monitors to say to the drivers, hey, you are driving like a hooligan. You're wearing out your brake pads in the 99th percentile. If you stop driving so quickly and stop decelerating so quickly, you might be able to save this amount of money, so on and so forth. But that's now how we start using a reliability life model to make better decisions. If we compare that to the shorter, fatter PDF for me, just focus on miles, you can see the huge discrepancy, which is why we as reliability engineers should always have an eye on the reliability life model, because they help us understand when our system fails. Now, they often do a better job when we use, but we often do a better job, I should say, when we use our brains when we create reliability life models. So it's all well and good to have reliability life models based on mileage, because that suits our needs and it's very simple. But if we actually think about how brake pads wear out, for example, understand that it's all about energy and not distance, then we make better decisions. So reliability life models, or at least understanding reliability life models, even if we don't go into full analysis mode, help us make better decisions. And when it comes to reliability life models, we tend to have a really basic continuum. On one end, we have what's called mechanistic models. And those mechanistic models are based on a physical understanding of how that failure mechanism propagates. And so we know the why and the how. We know what starts it. We know the failure mechanism, which is going to be corrosion or creep or diffusion. We know the environmental factors which influence that failure mechanism, like humidity and temperature and vibration. We know the material properties, which include things like grain size, strength, and melting point. And those things that cause our failure mechanism to start, which are faults, we have a good understanding of what it is that starts them. So if we, for example, we can use our knowledge of fatigue to know that if we want to minimize fatigue in a metal strut, we need to try and eliminate surface scratches and material imperfections. We can have a polished surface. We can have internal radii, which are relatively large, so we don't incorporate stress concentration factors. So just knowing what the reliability life model is, without having to go through any data analysis, means we make better design decisions. At the other end of the continuum, we have purely stochastic or random reliability life models. And that means we need lots of data to understand them, I should say. And there are times when that's more than okay. But there is a trade-off. You need more data to be able to create a reliability life model. And that's where lots of these probability density functions, probability distributions can come into play. Technically, if we assume a model, if we assume a Weibull distribution, or if we know it's because it's fatigue, we're going to assume a log normal distribution, or if we know that we are modeling the wear of a tire, then we're going to use the normal distribution. As soon as we start using that knowledge, which is great, we are introducing a level of mechanistic understanding. So even just the act of selecting the right probability density function means that we're not entirely stochastic. If we are entirely stochastic, that's when we just use what we call Kaplan-Meier estimation, where we just have no preconceived ideas. We're not fitting bell curves or Weibull distributions, but you need lots and lots of data points to create things like a cumulative distribution function. That's purely stochastic. No assumed knowledge makes up our reliability life model. And at the other end of the spectrum, where we have our mechanistic model, we have to rely on our understanding of the physics of failure. And of course, there's all sorts of things that lie in between. So for example, if we combine our physics of failure with our selection of our probability distribution, then we continue to move up this continuum. We start moving closer and closer to that mechanistic end of the continuum. We know through experience that many failure mechanisms have particular probability distributions which do a good job of modeling time to failure. And in between, we often use a combination of physics of failure to perhaps understand how we can characterize a typical life, but then incorporate an additional probability distribution to take into consideration some uncertainties. So depending on your scenario, you need to work out which approach is right for you. And just because you focus on a mechanistic reliability life model for like fatigue, that doesn't tie you into lots of data analysis. Simply knowing how your product can fail is very, very informative and useful for designing a product that won't fail. So before I move on, are there any questions about this continuum of reliability life models? None so far. Fantastic. All right. So let's go to one end of the spectrum, and then specifically, let's look at a classic mechanistic model. A mechanistic model is sometimes overwhelming, and we're going to go through a bit of overwhelm to make the point. I'm going to go through some equations. The idea isn't to walk away from this conversation with a photographic memory of these equations, but it's just I'm going to give you an example of how, if we're really interested in understanding a particular failure mechanism, how we could potentially model it with a very high level of precision. So we're going to look at creep. Now, creep is a failure mechanism which often gets overlooked. And you can see creep happening here with these glaciers, which are solid solid material that are slowly deforming over time. There's no additional mechanism here. It's just simple. It's a simple case of something which we assume to be solid somehow deforms over time in ways that can really ruin our day. And this is what we call creep. It's a tendency of a solid material to deform permanently under the influence of mechanical stresses. So creep can, again, ruin our days in many, many different ways. So let's look at this aircraft engine with the turbine blades going at rotating at a high speed in its center. And obviously this creates a centrifugal force, which means that these blades are now under that stress we talked about. And if creep's going to happen, this will mean that some of these turbine blades will get longer, which means that those ones that get longest the fastest will potentially hit the housing around the turbine and start to wear away, which means that our turbine becomes unbalanced once we have some turbine blades longer than the others. And that will then potentially introduce cyclic stresses in the middle of our, at the hub of our turbine, which then could lead to fatigue failure. So you can see how creep can quite literally creep up on us and perhaps create additional failure mechanisms perhaps trigger additional failure mechanisms that weren't on the radar, so to speak. So one approach to studying or analyzing creep, if this matters to you, is to do some purely a random or stochastic analysis. And the way we do this for creep, at least, is to get samples of whatever it is we're studying and then subject it to different loads, which we characterize using what we call the stress intensity factor. And that's one way of working out how we are stressing a piece of material regardless of size or shape. And then we can, in a test or an experiment, we can see how fast cracks grow, because creep will also create cracks over time. We can examine how fast cracks will grow and perhaps plot the experimental data on a chart like this. And this is experimental data from 4340 steel in dehumidified argon at 297 Kelvin. So it's dehumidified, so we've eliminated any other sort of mechanism like corrosion, which usually needs moisture to happen. Now, if we're going to go purely stochastic, we can perhaps conclude that there's a straight line. The experimental data creates a straight line. We can use some more statistical mumbo jumbo to create this 95% confidence interval, which means that based on this data, if we assume that the underlying model creates a straight line in this semi-log axis, then this confidence interval is going to appear. Now, this is one approach. Another approach, like I said, is to use those mechanistic models we talked about, and perhaps this involves going to a library or reading a journal or searching a journal to try and find if anyone has studied creep crack growth. And when you do, you might come across this tensile ligament instability model. Now, the tensile ligament instability model, or TLI model, it can be really useful when helping us try to understand how cracks will grow when exposed to creep. And it's based on the reality that material is not perfect. The steel we're examining has lots of imperfections and defects in it. I just made up a new word called deperfections. We might have to try and write that one down, Fred, and keep it in one of our next textbooks, deperfections. And then what will eventually happen is, as a crack grows, it will then move from defect or void or inclusion, meaning that at the tip of our crack, we have essentially a series of ligaments. These act like columns, which are the only thing stopping our crack from growing any faster. And because these ligaments, or these little narrow connections, are at the tip of this crack, they get stressed more than the rest of our material, which means these are going to grow over time in what we call the plastic zone. And if we know our material well enough, we can estimate the typical distance between adjacent voids or defects. Now, Before I go on, you're going to see some complicated equations, which you are never authorized to use because they're just used they are exceedingly complex, exceedingly complicated, and apply to a very specific scenario. But I'm just trying to take you through the motions of, if you were going to the nth degree to try and characterize some failure mechanisms, it could become as complicated as the gump you're about to see. So our tensile ligament instability model, which some bright young things in a university came up with when they started examining the physics of failure of creep crack growth, they came up with this model here based on a good deal of research and their understanding of the material itself. And you can see here we have an expression for the rate of crack growth with all these different parameters and material properties and environmental considerations on the right-hand side. And the correct response to this equation is, holy cow, that's a very complex equation. But there are still some terms which we don't have in this equation. And that means we need to do some more research and come up with, find that there are additional models. In this case, some other bright young things from a university have managed to characterize the average distance between adjacent voids for steels. Another team of bright young things have come up to create this rate of strain for certain stresses. And yet another team of bright young things have come up with this particular model, which helps us characterize the stress intensity factor, again, based on material properties. And now you have to substitute all these different models and equations into the master tensile ligament instability model. And when you do that, you do quite sophisticated analysis, we're able to go back to our experimental data. And instead of having this stochastic model, which has a straight line and a 95% confidence interval, we come up with this model here, which, because it involves so much more information through the research that those bright young things have done, and combine it with their experimental data, we have this very, very tight or small confidence interval, which is characteristic of a lack of uncertainty. And not only that, we can see that the mechanistic model shows distinct behaviors and characteristics that a stochastic model doesn't potentially want to uncover. We can see that the rate at which our cracks grow with respect to creep failure mechanism, doesn't create a straight line in the semi-log chart, which is exactly what we see from experimental data. But this equation over here, like I said, is a bit of a mouthful. And one of the people who often make it into my lessons and webinars is this guy here, the ponderous professor. He is one of our enemies of reliability engineering, who loves equations like this and turns what should be reliability engineering into reliability purgatory. But the overwhelming majority of normal human beings don't like these equations. So what can an understanding of a mechanistic model do for you? Well, first thing is we need to start breathing and don't worry. We only need to use mechanistic modeling sometimes on the vital few, not absolutely every way your system will fail. We're not interested in doing university level academic studies every single time. And a FMEA, for example, is really helpful at understanding which things might be candidate parts or mechanisms for further study. But even if let's just say that you have done a FMEA, or you've otherwise come to the conclusion that we really do need to understand creep cracks because that's going to be a potential way our thing can fail, then we don't necessarily need to, we still don't necessarily need to go through the full process of coming up with a mechanistic model. Engineering judgment is a really useful tool. But let's just say that we are really worried about creep crack growth. Well, we can still look at a physics of failure model, and as opposed to trying to solve that equation, we can just simply realize or use this equation here to understand that there are, in this case, I think 8 different parameters which will govern how fast our creep crack growth So a creep crack will grow over time. And this can at the very least work out which material property we want to see in our steels that we're going to get from the third-party supplier. If the strain hardening component will accelerate creep crack growth, then that is useful information. So you're going to select a steel which will have perhaps a low strain hardening component. So we don't need to solve the equation just to simply understand what the generic role these factors play in accelerating or decelerating our particular failure mechanism. Again, the example I talked about earlier is we don't need to do a full fatigue analysis or fatigue study or fatigue experiment if we simply need to know how to design fatigue out of our system. If we have smooth surfaces, if we try and make sure we have no defects, if we have a large radii so we don't concentrate stresses, if we're still really concerned, we can perhaps shot peen those areas where fatigue is going to be highly likely. And without having to do a full university level of study, we have already incorporated a bunch of wonderful corrective actions because we know the mechanistic model. So that is an example of what can be a mechanistic model at the far end of our continuum, but more often than not, we just need that generic understanding of how our thing's going to fail. But also be aware that if you're interested in things like accelerated live testing, then you need to know that mechanistic model. You can't get away with trying to stress your system to higher stresses to try and truncate your test duration unless you have a physics of failure model ready to go. But once you do have that physics of failure model, then it allows all those wonderful things like ALTs and prognostics and condition-based maintenance. And of course, knowing how a thing fails helps us find root causes, which are what we're trying to design out of our system. So some of you might have heard of accelerated live testing or ALT. And when I said that you need to have an understanding of the physics of failure to do ALT and then saw that physics of failure equation for creep, you might have been very concerned about how complex or how complicated ALT or accelerated live testing can be. And the answer is, to this question at least, does it have to be this complicated? The answer is no. We really want to leverage our understanding of reliability life models to truncate test duration, but it doesn't have to, you don't have to do a full peer-reviewed study of creep crack growth to get there. So let's go through an example. Let's go through a scenario where a system you're designing is going to fail perhaps through a chemical reaction. And a chemical reaction involves a bunch of reactants that go through a chemical reaction to produce products. And typically we want our system to be all reactants and no products. Products represent degradation or damage. So you might recall from basic chemistry classes at school that as a rule, a chemical reaction involves converting the energy level of one state of material to an energy level of another product state. And the idea is that there will be a tendency for your material to assume a lower energy state. We might spend a lot of time and a lot of money creating wonderful steel, but over time, Mother Nature wants that steel to revert to a lower energy level, which is corrosion or corroded material. So that's the energy level of our reactants at the start of our chemical reaction. And here is the energy level, much lower energy level of our product. But there is a little catch, and that is in the middle between these two states is what we call activation energy, because these reactants need a little bit of a kickstart to commence the chemical reaction. And once we do have this activation energy, our chemical reaction will then release energy back into the environment around it. So if we start the chemical reaction, it can become self-sustaining if the energy we create then creates enough activation energy for the molecule next to it to do the same thing. So a basic example is corrosion. On the left-hand side, we have a beautiful representation of reactants. And on the right-hand side, we have a beautiful representation of corrosion. And this is all a chemical reaction. Now, there's a smart guy who studied this particular idea of chemical reactions, and he worked out that as a rule, we can characterize how fast this chemical reaction occurs if we know that activation energy and if we know the temperature in degrees Kelvin and use this thing called Boltzmann's constant, which is that figure you can see on the screen right now. So if we're able to somehow measure activation energy and combine it with a unique constant for each chemical reaction, we can then understand how fast our chemical reactions are occurring. Now, some of you might be going, oh, great. If I want to use this equation, then I need to do an experiment to somehow characterize this constant, somehow characterize this activation energy. I don't do chemistry. This sounds too complex. I'm going to go home. And that is a somewhat understandable response to this equation, but there is an easier way of using this equation to help do things like accelerated life testing. What that means is that we can start manipulating this equation where we, instead of using the rate of reaction, we can replace that with another constant divided by some sort of characteristic life, as in the longer your thing lasts, the slower the reaction or rate of reaction. Now we can keep manipulating, and eventually come up with this equation, which will give us a straight line if we plot stuff in a certain set of axes. And you can see we usually familiar with the concept of y equals mx plus c is the equation we use for a straight line. And this doesn't look quite like that yet. But it actually does align with that basic equation for a straight line. And what that means is we can come up with this really weird chart or this really weird set of axes that if we have the characteristic life expressed logarithmically on the vertical scale and the negative of the inverse of the temperature on the horizontal scale, all chemical reactions should create that straight line. So you can see on the horizontal scale, we have these temperatures here in terms of degrees Celsius. And this allows you to go and do testing. So let's just say you are trying to choose or differentiate between two different types of rubbers. And your use scenario involves a temperature for your system, which includes these rubbers of about 40 degrees Celsius. Now, if you increase the temperature for tests and see how long it takes for this rubber to fail, or peroxide cured rubber, in this case, to 140 and then 150 and 160 degrees Celsius, we get these times to failure here, which create these three data points on our Arrhenius plot, which mercifully create a relatively straight line. Let's just now try and say we're not trying to accurately measure reliability. We're just trying to use accelerated life testing to differentiate between this rubber and another rubber. So we do the same test, and this time with sulfur cured rubber, and we get these data points, which creates this straight line, which then allows us to, for example, work out that our best guess for sulfur cured rubber in terms of its time to failure is about 170 years at 40 degrees Celsius, compared with peroxide cured rubber, which has 1600 year time to failure, indicative time to failure at 40 degrees Celsius. Now, these might seem like fantastic numbers or fantastical, 1600 years, 170 years, my system's not going to last that long. But what we have done very easily and very quickly is firstly confirm that, hey, both rubbers should be more than okay for our scenario. And by the way, if I had a choice and all other factors were equal, if both rubbers cost about the same, I'm going to use peroxide cured rubber because it lasts longer as a general rule. And that means that by using this test, based on our physics of failure understanding, we don't have to do a lot of testing. We don't have to spend a lot of time getting these test results in order to be able to say something about how long our thing is going to last in the real world. And this all comes back to the reliability life model, which our good friend Arrhenius created for us back in the day. We also know that because the rate of degradation is somewhat constant, that we, if we want to, can use bell curves to characterize the uncertainty we have in these times to failure. And that's the subject of an entirely another webinar that deals with how we use uncertainty and how we use stochastic models in accelerated live testing. But if the decision you're trying to make is which rubber do I use, then this is a very powerful tool which doesn't take a lot of time. All because we know the physics of failure, and if we see these straight lines, it provides us evidence that the Arrhenius model is a good model for whatever's going on. So, but if we do use those, if we do come up with a way of using this bell curve to characterize the uncertainty in times of failure, that's where we start to combine our physics of failure modeling with a probability distribution. And that's where we can combine models and come up with really useful ways of characterizing the reliability of our stuff. But perhaps you don't have lots of data and don't want or need a physical model. Well, that's okay. So perhaps you do have lots of data. And one example where we do have tons of data is fatigue. Now, fatigue is the bane of our existence as reliability engineers, and fatigue is one way of making something fail without ever having to expose it to a stress that exceeds its strength. A lot of materials will eventually fail if they're subjected to repeated stresses that are well below their strength. And eventually a crack will grow over time to a point that the crack reaches what we call a critical length, and then whatever's left of our strut or our member doesn't have the strength to repel or defeat or accept the challenge of this much reduced stress, and we get catastrophic failure. Now, whenever we have a new alloy or new steel created, it is subjected to all sorts of fatigue tests in laboratories across the world. In fact, we have hundreds of thousands of data points of fatigue experimentation for virtually every type of steel. And here you can see in a laboratory where we have a sensor on a steel strut being exposed to cyclic stresses, and it will keep going and measure how many cycles this steel is exposed to before any fatigue cracking causes it to fail. And so we have, in this case, plenty of data, but this is not a common occurrence. And we know that for fatigue cracking in particular, that the stresses at the tip of the crack are amplified because of the geometry of the crack tip. And so we have, again, another plastic zone, which is characterized, or which is based on the stress intensity factor, which we looked at previously for our creep crack growth. And the speed at which the crack grows, we know through experience is proportional to the difference between our stress intensity factors for each cyclic load raised to a power of m. So this represents the cyclic change of our cyclic loads as they're being repeated to up and down stresses. And because through experience, we should say, we know that there's this exponent m, which has this sort of multiplicative effect on time to failure. Now, anybody who's done any sort of statistical analysis knows that the log normal distribution is fundamentally based on the multiplication of different random variables or processes. So it just so happens that we also observe that the log normal distribution does a fantastic job of modeling time to failure for fatigue. And all that data we talked about can be plotted on a chart like this, where we have a semi-log plot. And if we have laboratory or after laboratory doing fatigue testing on specimen after specimen, we can essentially create a chart which has so many data points that we don't need an underlying model to create a line of best fit along with confidence bounds. We simply just have so much data, we can create this sort of model here based on inspection only. And we can also see through experimentation that for most steels, there's this thing called an endurance limit. That is, if a stress is low enough, it won't cause any fatigue crack growth, which is not a phenomenon we observe with aluminium or aluminum. And so this chart here is a very famous type of chart. On the vertical axis, we have stress, in this case represented in megapascals, and that is often shortened to simply S. S stands for stress. And on the horizontal axis, we have the number of cycles, in this case, N. So this is what we call an SN chart. And most steels will come with their own SN chart. And if you're interested in, for example, understanding how long it's going to take for your strut to fail if it's exposed to a stress or an average stress of 400 megapascals, cyclic stress, I should say, then your best guess at the median fatigue limit is 87,000 cycles simply by using this chart. And we need to remember this is always logarithmic. So this is an example where we just use lots and lots and lots and lots and lots and lots of data to create a model. There is no preconceived normal distribution or bell curve. We just get lots and lots of data. But so this is what we call a non-parametric model, a random model without a probability distribution. But here's a trick. We can add information if we assume a probability distribution. And when we do that, we get a lot more information. But if we want to do that, we need to use a lot more data. Okay, so we get, just coming back to our, thanks, Fred. Coming back to our fatigue example, where we have lots and lots of data, but there is scope for us to actually add a ton more information if we do incorporate for example, probability distribution. But the thing to remember from fatigue, for example, is that if you're going to create a model based on this SN curve, then you need lots and lots and lots and lots of data. So if you don't want to use a model, then you need to pay for it through lots of data. So let's have a look at, for example, a handle on a door lock. Now we might start with, if we have this handle here, we might be designing it. We start with finite element analysis to work out that we have a point of localized high stress at this internal radius of our door handle. And this is where we're going to be, for example, concerned about fatigue cracking, because there are lots of door openings. We open the door quite regularly, so it has this cyclic stress. And let's just say finite element analysis identified a typical stress of around 500 megapascals. Well, we can go to our SN chart and work out with a 90% confidence interval that's been provided to us by lots of experimentation, I should say. And if we look at, if we zoom in and we look at 500 megapascals, we can then impose or create, overlay a normal distribution or log normal distribution, because of logarithmic scale, based on our understanding of how to transform this 90% confidence interval into a log normal distribution. And that means that we can use this probability density function here, which again is a subject of another webinar or another lesson, to work out the likelihood of our door handle surviving 100 openings and shuttings, or 200, or 300, or 400. And that could be really useful information for working out what your warranty period should be, or if you should launch your product in its current design at all. But as we know, when we open a door handle or we open a door, the amount of stress we use each time can vary. Some people are strong, some people are rough on door handles. And so it's not always going to be 500 megapascals each and every single time. So what happens if you're faced with a scenario where you have more than one stress level? So let's just say that if we go back to our scenario where instead of it being 500 megapascals all the time, let's just say that we are going to assume that we have two stresses our door handle will be exposed to, one of 400 megapascals and another one of 600 megapascals. Now, if we were to use 600 megapascals, then we have a median fatigue limit of about 10,500 cycles according to this chart. And this is where things can sometimes get murky in the world of reliability engineering, because there's lots of what we call rules out there for how to incorporate damage being accumulated at different stresses. And they're called rules for a reason. They're not called theories, they're called rules. And one of these rules simply involves trying to divvy up or have different rates of assign different portions to different stress levels. So for example, if we assume that now service life of our door handle, it's going to be exposed to 7,500 cycles at 600 megapascals, then based on our SN chart, when we convert it back into the uniform scale, this will take up about 50% of the fatigue limit of our handle. If we also assume that our door handle is going to be exposed to 30,000 cycles at 400 megapascals, well, that's going to take up 34% of this bar here, which represents 34% of the fatigue limit being used up at that particular stress level. And if we add these two rates these two fractions of damage or fractions of fatigue life being taken away, we get 84%. And that means that 75,000 cycles at 600 megapascals plus 30,000 cycles at 400 megapascals means that the fatigue crack in our handle is about 84% of the way there. And this very basic approach is based on what we call Miner's rule. It's used a lot in reliability engineering, sometimes used a lot, too much, I should say. And we call something a rule when there is no real scientific basis for it. It's just a rule that people have come up with, and in some cases has shown to be relatively useful. The idea is that we sum the total number of cycles at a particular stress level with fatigue limit, or how long it's going to take for your thing to fail regardless of the failure mechanism. And we add them all up, all these different stress levels all up. And where we typically would assume that a failure will occur when C equals 1 or 100%, experience has shown that it can sometimes be between 70 and 220%, which means that this is not entirely useful if you don't know how your system or your material is going to behave. So the reason I include it here is that most reliability life model discussions include things like what we call damage models, like this Miner's rule. But you need to be very careful with these because there is a lot of just basic assumptions, or just not even assumptions, just things that are assumed to be true. That's an assumption. I heard it when I said it. But without any scientific basis or theory behind it. And so this is what we call a damage model, which can be useful if you validate it for your scenario, but is not always going to be useful. So if we go back to these probability distributions, the thing we talk about a lot, I should say, in reliability engineering, are things like Weibull distribution this, and normal distribution that, and bell curve this, and skew this, and constant hazard rate that. So some of the things that we often do as reliability engineers is try to find or fit a probability distribution to whatever it is we observe. And sometimes we don't have enough data to do that, and that's okay. But sometimes it's very useful just to know before you start examining your system which probability distribution is going to work for you. And so just a simple understanding of the reliability life model, if it's, for example, fatigue, then the log normal distribution could be the right one for you, or should be the right one for you. And you've saved yourself a ton of experimentation trying to confirm what we already know in the field as truth. So I'm going to leave this conversation here for today. We started off today when I showed you that really wonderful example of brake pads, brake pad wear, and how Ford in particular is doing some really funky stuff that to help them better predict how long it's going to take for their thing to wear out, their brake pads to wear out. And that means that each vehicle can track or estimate how much wear is going on in those brake pads without having to use things like condition-based maintenance and sensors, which are notoriously difficult for brake pads in particular. And when we have a better understanding of reliability life models, even if the underlying physics and theory can be quite complicated, all we might need to know is which lever we need to pull to increase the life of or time to failure of our system. And that's all we have to concern ourselves with if we're making our first design a reliable design. So with my camera back up and running properly. Apologies for that heinous exhibition of unprofessionalism. Are there any questions or comments, queries, theories, rules, scenarios, anecdotes? Anything at all? Thank you, Maximilian, for the comment about the continuum. Much appreciated. Philip, what reliability models would you suggest for mobile assets? Could you explain that? When you say mobile assets, you're talking about vehicles, for example? Forklifts and vehicles. Okay, so I mean, that's a very broad question, and obviously your forklift in your vehicle is made up of a bunch of different components. So depending on each component, or each component will have its own reliability life model. So for example, I think, correct me if I'm wrong, Fred, but we know that bearings, bearings are pretty well modeled with a Weibull distribution with I think a shape parameter of about 1.7, I believe. We know that, for example, log normal distributions do a great job for fatigue. So for me to answer that question, you'd have to tell me what the weak points of that forklift are in terms of components. And of those components, those vital few components which drive reliability characteristics, what are the dominant failure mechanisms? That's what I would need to be able to answer that question. So for you to be able to get on top of modeling the time to failure of your mobile assets, forklifts and vehicles, you need to understand what those design weak points are, or the maintenance weak points are, the lowest hanging fruit, and those are the components whose failure mechanisms you need to characterize using a model. Let's just see. Oh, there's a bit of frenzy of conversation. So yeah, Fred just said we always need to sort out the failure mechanisms involved. So it's there's no simple answer to that. You'd have to work out what it is that's driving your driving failure. Louis said each component and each failure mode, right? And I think you're sort of confirming. Sorry, you're responding to Fred. Yes, you'd have to know each component and each failure mode, but that is overwhelming. So you need to have an understanding of which ones are the dominant ones, and they're the ones you model. Nelson asks, thanks. One question is, how does parameter estimation for your models fall in the continuum when you add expert elicitation? So it's like Bayesian sort of stuff where you are, for example, your experts know through experience that, I don't know, when you do a Weibull analysis, those bearings tend to have a shape parameter of 1.7. That is not to be wasted. That's not to be trivialized either. And there's a whole field of analysis out there, which is sort of Bayesian, called Y-Bayes, where you have that specific phenomenon where you know how certain things fail. You bring that pre-existing information into your models, and then that improves your reliability life model. All you're doing is introducing an element of the physics of failure. So what happens if you presuppose through, or if you conclude that this probability distribution with this shape parameter over here through expert judgment is likely going to describe time to failure for your bearing, then you're introducing the physics of failure into that model, and it starts to move along that continuum towards a mechanistic end. And the good thing is, when you use expert judgment, as long as it's elicited in the correct way, you get that physics of failure understanding without having to do testing. So it's almost free in a way. Kevin asks, I analyze component fatigue data on a regular basis and generally run the data through multiple distributions, 2-parameter Weibull, 3-parameter Weibull, and log normal. I generally use a best fit via Anderson-Darling using MLE estimates. Is it the best approach to use the best fit, or use the known log normal? It's not wrong to assume the log normal. However, I don't think it's a bad thing to satisfy your curiosity to see if there's any other better distributions out there which can describe what's going on. That said, when you do fatigue testing or any sort of reliability testing, you're observing a random variable. So any minor perturbations in or any sort of variance in the test you observe on that particular day might trigger a two-parameter Y-ball being a slightly better fit than a log normal and vice versa. I think Fred quotes a huge amount of data you need to have to be able to differentiate between a log normal distribution and a Y-ball distribution with a shape parameter of 2.5. So my answer is going to be slightly nuanced. If you don't have a lot of data, then using the model of best fit can be slightly misleading, especially given what we know about fatigue. We know that the log normal distribution is fantastic, and it's a chance that that particular test creates that data set, which might on that day suggest the Y-ball distribution is the way to go. But unless you have tons of data to back that up, that then goes against what we already know or already observe for fatigue. So I hope that answers your question a little bit. If you want to explore that conversation more after this webinar, I'm more than happy to do that. Okay, Maximilian asks, on the forklift, lots of questions coming in, so you moved out of my window. Let me get back up to you. On the forklift vehicle subject, those driving failures can be sorted out early in the development process with the first prototypes, or maybe FMEA, FEA. Am I correct in that thinking? Or am I missing any failure identifying activities? Tell you what, you've come up with some really good ones there. If you have not got field data, you have done a really robust FMEA, I would be amazed if the vital few, if the top few failure modes and mechanisms in your FMEA don't also turn out to be your key drivers for reliability of your forklift and vehicle. FEA usually, I prefer to use FEAs after you do a FMEA. So for example, if your FMEA identifies fatigue cracking as a concern on the inside of your handle, then one of the corrective actions of a FMEA could be to conduct finite element analysis on that handle. So the analysis itself follows on from your FMEA, which identifies that as a concern. But once that sort of process you're describing is all about trying to predict the likely failures before we create that first prototype or before it goes into the field. And as a rule, if you do a FMEA properly, if you do your reliability engineering well, you won't be far off. Louise said, it was brief, but I liked your comment about using FMEA to sort the fewer significant failure modes to dive in. I use the term vital few a lot, as does our good friend Carl Carlson. Fixing the trivial thousands is over-engineering that makes your product bigger, heavier, more expensive, go through more energy. We want to only focus on the vital few, and that's what reliability engineering is all about. And that also saves us a lot of stress because we're not fixing everything. Derek Lee said, fantastic presentation. Thank you. Always enjoy your clear and insightful approach to explaining things. Oh, so that wasn't a question, it was a compliment. Thank you very much. Much appreciated, Derek. If there's any more suggestions about what I could do better or more topics, feel free to keep them coming my way. Nelson asks, one thing to ask is that in design, I see we do the FMEA to know failure modes, importance in maintenance environments. So I see the CA done first with the maintenance data used to find the significant failure modes. What is your experience? Hopefully I understand your question well enough, but I like using FMEAs as part of the RCM maintenance approach or whole maintenance strategy process. I like not having a clear demarcation between FMEAs and RCM as we do later. An RCM, which is reliability centered maintenance, which is sort of the formal name we give to the reliability engineering activity of trying to come up with the best maintenance strategy. Essentially, the first part of an RCM is to conduct a FMEA or a FMEA. And if we can somehow do our best at keeping those two concepts linked, it means we're more likely to think of our maintenance strategy as part of our design. I'm not sure if that's close to where you're going with that question, Nelson, but I really counsel people I speak to against doing design over here, design, and then think about maintenance. We design for maintainability. Maintainability doesn't just happen. And I've seen plenty of examples of us designing something without thinking about maintenance, and it turns into an unwieldy, unsupportable mess at the other end. Arun asked, do we have a research paper on the comparative study of the type of distribution models used in the same data set and the results from it? I vaguely remember coming across it some time ago, but appreciate much if anyone can share info. I can't quote research papers by name in this conversation, but I certainly know they exist. I would dare say a brief Google Scholar search of fatigue and log normal would inundate your search window with all sorts of interesting papers on that topic. And same with Weibull and anything else. In fact, the very first paper which we all go back to for the Weibull distribution is the one published by Willotti Weibull back in 1951 and 1952, where he made the point of saying how the Weibull distribution with certain parameter values does a really good job of modeling a bunch of non-reliability processes and a bunch of reliability processes as well. So perhaps that's the first paper in that little industry you're referring to. Okay, so that's comments. I haven't looked at the question bar for a bit. Where are you, question bar? So I've just appeared to have lost my question bar. So if anyone's asked a question, I'm unable to see it right now. I'll do this thing again. There it is. Okay, so someone asked, what is the best model for film and electrolytic capacitors? Thank you so much. Okay, so I need to have more information to answer that question, but if you're looking at things like diffusion or what some of the common or usual suspects in those sorts of things, the Arrhenius model is usually pretty good, because that again models a chemical reaction, which is a lot of what goes on in the degradation of electronic components. So I can't answer specifically unless you give me the failure mechanism, but the Arrhenius model is not the worst first step when trying to come up with an answer to that question. Kayvon asks, Chris, I think your excellent example of truck money supports selecting a correct failure mechanism function to model. Brake shoes wear is not a function of mileage. Yes, it's not a function of mileage, but it's unfortunately sometimes miles is the only usage metric we have. And for many years, it was the only usage metric we had. So it was imperfect, but we had to use it. And until recently, we just did not have the ability to track the amount of energy we were dissipating through our brake pads. So it just goes to show that miles or distance or kilometers can be the state of the art in one decade, but as we evolve as an industry, as our reliability engineering expertise grows, we need to adapt and change. Okay, going back to the comments. Okay, thanks for your thoughts, said Nelson. Your angle was on the order of operations, one before the other. So hopefully the FIA, finite element analysis, and then subsequent investigation activities, hopefully that answers your question or provides the information you need. And Kayvon makes a good recommendation in regard to some of the, as opposed to going through papers to try and find which distribution works the best, there are some textbooks, including O'Connor's textbook in the chat window, which does have some commentary in this space. And another one is reliability physics and engineering. I could make a plug for a textbook that I co-wrote with Mohammed Badaris and from University of Maryland, which is all about probabilistic physics of failure, where if you do want to go through the process of understanding which accelerated life testing model you need to use, then that textbook sort of goes through every single one we know. So that's out there as well. That's a little bit higher level, a little bit advanced. And if you are really serious about doing that, then perhaps you need to look at it. But if you're just trying to have some educated guesses to make some good decisions early on, there's plenty of free resources out there as well. Any more for any more? This week, I also debuted a new microphone, a lapel microphone, which is more expensive than my house. So hopefully the sound came through pretty well. Oh, thank you, Kevin. If the sound came through pretty well, if there's any issues with sound, please let me know, because this is again my first time using this microphone. Thank you, Louise. My apologies if I mispronounce your name. Oh, one of those was right. Okay, if anyone wants to reach out after this webinar to discuss these issues further, as a lot of people tend to do, feel free, don't be shy. I'm more than happy to continue these conversations, because both of us learn more about what's going on. Any more for any more? Okay, Fred, I think that everyone who's wanted to say something has had a chance. And again, if you think of something straight after this webinar, please feel free to reach out via email. You've got to ascendo reliability.com, so I know you know how to find my contact details.